started. Okay. All right. I'm actually, hold on, give me 1 second. I actually want to pull up the lecture notes from last time because there was something I kind of wanted to bring up. But now that I've got this up, I'm going to draw something up here on the board and then talk while I'm drawing. I'm going to bring something up regarding the example that we did in class on Friday. But anyways, you all do not have a homework assignment due today, okay? You do have a homework assignment that is due on Wednesday, okay? That's this assignment which I've given you, which, I mean, I'm not trying to be dramatic when I say it, but it is one of the more difficult assignments in the course, so much so that today's lecture is really just going to be not really tips and tricks for a homework. I don't really want to teach that way, but there are some strategies that you can use in general to make the computation of support or computation of beam deflections easier. And so that's going to kind of be the start of the show for today. One thing I will say, so on Friday you have 2 homework assignments due, but the first one isn't really a homework assignment. All I want you to do is install Mathcan and upload a screenshot that is installed. Like, that's it. So if you've already done it, then that's a pretty simple assignment. Just basically open Mathcan, have it running, take a screenshot of your desktop, submit. That's the homework. It's that simple. Okay. Homework 6.4 is the frame assignment, and that's the last one. Okay. That's going to be the last one before the exam. What I'll probably do for that assignment is give you the solution on Saturday, so you'll have something to study in preparation for the exam on Monday. Okay. Speaking of, you do have homework 6.2. I did want to give you like a slight hint or something. As we mentioned, I came up with homework 6.2 off the dome. The deflection and rotation value that you're going to get on problem 1 if you do it correctly is going to be kind of high. Now, that's not to say there's anything wrong with the problem. I mean, it's a very long cantilever beam with a lot of force on it, so it's going to deflect quite a bit. But if you get a large number for deflections or a large number for rotations, don't think that that's an error. You're probably doing it just fine. Okay. Okay. All right. So everybody get the code? No, that's fair. I was a little confusing about that. That's fair. Okay. All right. Everybody get the code? All right. I did want to mention something about the example that we did in class last time, and I've got something here drawn on the board. Just so you're aware, this is sort of like a quick schematic of the problem. So it's 1.2 kips per foot, and what we were trying to do in the problem was determine deformations at this point B. We just sort of picked point B for the purposes of the problem, right? So what did we say? We said that, so the beam is what, 30 foot long? So we said that this point was 10 foot and this point was 20 foot, right? Okay, and we did the math, and what did we get for our, so this is point B. Somebody remind me, what did we get for deflection at B? What was it? What was the value? I think the rotation at B was something like 0.223 degrees. Something like that. Is that right? What did we get?
0.792 down.
Okay. Now, that was a pretty straightforward problem. One of the downsides with the solution, though, is it only gives us the deflections at that particular point, okay? So what happens if I want deflections here, or I want deflections here, or somewhere else along the span? That does make the problem like a little bit more challenging. And in order to do that, we're going to have to start defining things sort of as a function of x, okay? And that can get really confusing from an integration standpoint. So what I would say is that if you want deflection anywhere, or rotations anywhere, the suggestion that I make is to introduce a new variable called A. So that would make this 30 foot minus A. And then you're still integrating in terms of x, but if you know how if you perform a definite integral in terms of x, the x vanishes. You want the x to vanish, but you want this term to stay the same. So instead of getting deflection as a value or rotation as a value, you're going to get deflection sort of as a function of A. You're going to get rotation as a function of A. And you'll get like an equation, and you can plug and chug into that equation to get deflections anywhere or rotations anywhere. So if you go back to some of the problems that I discussed in shear and moment diagrams, let me go back to this. So I mentioned that just to show you, remember when we talked about aids for structural analysis, and I said, okay, here's how to derive WL squared over 2, or WL for maximum shear and maximum moment. If you remember that, one of the things that we sort of like ignored was, well, how do you do this? Like, how do you get deflection as a function of x? How do you get the maximum deflection or what have you? Well, you basically just do it this way. So you would just integrate, write your moment diagrams in terms of A, and then get an expression. So imagine in this expression, instead of an x, there's an A term. That's basically how you do it. I just wanted to throw that out there just to be sort of complete in the coverage of the topic. I'm not going to expect anybody to do that on a homework or an exam. Not that you can't do it, it becomes alphabet soup after a little while. So, and plus, they've already been derived. You can just look them up. So, does that make sense? Okay. Now, there was one thing I didn't get a chance to discuss with this example, and it sort of leads into the lecture for today, is I kind of want to talk about this. Okay, and I'm talking about this because you do have a problem on your homework assignment where there is a variable cross-section. There is a section that has like the moment of inertia changes along the beam, which, by the way, this is something that we do in the real world all the time. We do this a lot in plate girders where we make the plate girder deeper or have beefier flanges, for example, if we're talking about composite steel plate girders. We'll have beefier flanges and maybe thicker plates in the section that has higher moments, or maybe a bit more stiffeners in the section that has higher shears and what have you. So what happens if you have a problem like this? Okay. Well, first off, let's say I want to find the vertical deflection at C. I want to find out how much it's deflecting at midspan. Well, you're going to have two real moment functions, and you're going to have two virtual moment functions, right? Because think, what's the shear diagram going to look like? It's going to go up, over, down, over, up, right? And then the moment diagram is going to be a line and a line. So you're going to have two real moment functions that are linear, and your virtual moment functions are going to look the same way, okay? The problem, though, is your I values, okay? So we have two real moment functions, for example, that go from 0 to 22 and 22 to 44, but in between there, we have an interruption in our moment of inertia. So when we carry out the integrals, we have to split them up. So technically, this problem would require 4 integrals, okay? We have to integrate from here to here, from here to here, from here to here, from here to here, okay? And what I would say is that is considering what we've talked about up until now, okay? This would be sort of the brute force, systematic way of doing this problem, okay? But my goal for today's lecture is to talk about simpler ways of doing these problems. And I've got 4 different tricks I want you to keep in the back of your head when you're doing these problems, when you're doing your exam problems, when you're doing homework 6.2 and 6.4. And so let's get into that, okay? Today's lecture is going to be very story time heavy, very, slide heavy. I'm not going to do any in-class problems, okay? And all these notes are here on Blackboard, okay? So there's nothing here that's on the screen that you're going to miss if you don't get a chance to write it down. What I am more interested in today is that you really honestly receive the message that I'm giving you. So if there's anything I say that's confusing, that doesn't make sense, bear with me. Now, you're going to see a lot of algebra, a lot of equations here in this presentation, but the purpose is to ultimately derive some guidance that makes the process easier, not harder. Okay? All right. So, what am I getting at? Okay, I'm getting at this. This is our goal, is to carry out the computation of beam deflections using virtual work. So it requires a lot of algebra, requires a lot of integration, requires us to sum those integrals up. Okay? I don't know if there's anything else I can tell you to explain the concept. Like, the concept is the concept. We are comparing stored strain energy to external work done and comparing our virtual work terms to figure out deformations. And it requires algebra and integrals. Like, that's basically it, okay? But given the problem and given the severity of the problem, it can make things just rote to do, you know, calculation-wise. There's a lot of formulas, a lot of equations, a lot of integration. There are some tips and tricks that I can give you to make this easier. Now, I've got 4 of them for you, okay? I'm going to tell you what those 4 tips are right now, and then I'm going to explain them over the rest of this lecture, okay? So here's tip number 1. This is probably the most practical tip, and that is to exploit symmetry whenever you can, okay? And don't worry, I'll explain what each of these mean in detail, but exploiting symmetry will make your life so much easier if it's possible, okay? So that would be my first piece of advice. My second piece of advice is to use a coordinate system with its origin at the free end of the beam, okay? And this particularly applies to cantilevers and overhanging sections, but that's piece of advice number 2. Piece of advice number 3 talks about the samurai sword or the lightsaber when you're cutting a section. When you cut a section, always look towards the origin of your coordinate system. I am not talking about cutting a section and looking to the left. I'm talking about cutting a section and looking to the origin, okay? That's not the same thing, okay? If you notice something on the homework assignment that I gave you 2 problems. Problem number 1, I gave you an X and Y coordinate system axis. I did not do that on problem 2. That was not an omission. That was not an error. That was on purpose, okay? Because I'm going to be making a point about that today, all right? So we'll get to that here in a bit. 1, 2, 3, my 4th piece of advice is to exploit integrals that have a lower bound of 0, okay? And there is a very specific mathematical reason why, okay? You can probably sort of figure that one out, but we'll take these in step by step. Speaking of, like I said, we're going to take each of these step by step, okay? So my first piece of advice for you is to exploit symmetry, okay? As I said, the concept of virtual work is that we are summing energy. Ultimately, these integrals are there to sum the energy totally in the beam. And we can use that idea to reduce the number of integrals that we have to compute. For example, let's take this problem that we just talked about. We've got 2 real moment functions, 2 virtual moment functions, but because we've got this break in the cross-section, it requires us to have to do 4 integrals. One thing I do want to point out, by the way, look at the integration, okay? I have to multiply little m times big M, okay? So let's take the first 2 expressions. If I have to multiply this times this, what is 4x times x over 2? Somebody tell me.
Squared.
Say again?
2x squared.
2x squared. Okay, if I ask you how to multiply this times this, you can give me an answer. What if I asked you to multiply the bottom one times the bottom one? What are you going to tell me? Break out the FOIL, right? Because you're going to have to first outside, inside, last in order to do that. So just by its very nature, having to deal with these 2 is more challenging. Does that make sense? It's not hard. I mean, you can do it. I know everybody in here is FOIL, but it just takes time, okay? How can symmetry help? Okay, now we're going to have some math discussion. We're going to go back to Math 229. All right, so let's consider the following function. This is f of x equals 6x minus x squared. And I picked this equation for a very specific reason because this looks a lot like moment functions that we've been deriving so far. I believe for this problem, the real moment function was something like, wasn't it something like 18x minus 0.6 x squared? It really isn't all that crazy, right? I mean, this is the type of function we're going to be dealing with here. So let's consider this function. What happens when you graph that function? Well, it looks a little something about like that. That, to me, looks like a moment diagram. It crosses the x-axis at x equals 0 and x equals 6, okay? Now, if I wanted to compute the area under the curve from x equals 0 to x equals 6, how do you do that? How do I compute the area under this curve from x equals 0 to x equals 6? I'm asking.
Take the integral of the function from 0 to 6.
Take the integral of the function from 0 to 6. That is one way of doing it. Would you agree that this is a way of doing it? But does that work too? Could I take the integral from 0 to 3 and just double the answer? Would that work? Yeah, it would work because I would get half the answer and I'd double it. Is that a mathematically equivalent way of doing this problem? Absolutely. It also has connotations for us because those integrals represent energy. As long as we're summing up the total amount of stored energy in the system, we can integrate it however we want. Okay? Now, we can exploit symmetry if we have the following 4 constraints. Okay? So in other words, the problem has to be symmetric with respect to its geometry and its boundary conditions, which, for example, this problem right here, this problem is symmetric with respect to its geometry and its boundary conditions. Is it symmetric with respect to its loading? Yes. It's just a simply supported beam uniformly distributed load. Is it symmetric with respect to its flexural stiffness, EI? You bet. Where this problem right here fails is the last point. It's the beam has to be symmetric with respect to the point of interest. That's where symmetry really didn't work for this problem. Now, it would work for this problem if our point of interest was right here, where this is 15 feet and this is 15 feet. If this is the problem, if this was our problem, we could very easily exploit symmetry. That's where this one failed, okay? I mention this, though, just for the purposes of this lecture because this is a lot of what structural engineers deal with in the real world. They deal with simply supported beams subjected to uniformly distributed loads, and they want to figure out worst case bending, worst case shear, worst case deflection, okay? Here's my point, though. So let's talk about exploiting symmetry. Here's the old way of doing it. And the old way of doing it is to integrate from here to here, here to here, here to here, here to here, okay? 4 integrals. I propose that the new way of doing it is to just integrate from here to here, from here to here, multiply that by 2. And by the way, by doing that, I'm using these simpler functions. So the integrals that I'm carrying out are really easy. Just integrate this from 0 to 10, integrate it again from 10 to 22, multiply it by a different 1 over EIs. Okay? Does that make sense? This is my first tip to you, is to exploit symmetry. Okay? Now again, it only works if all 4 of these are true. All 4 of those have to be true in order to exploit symmetry. So there is a good chance that this isn't going to work. And I'll just go ahead and say it. It's not going to work on your homework assignment. Maybe it works on an exam, maybe it doesn't, okay? But I'm just saying, I don't know. But I'm saying if you have a problem that's symmetric, here's one thing I can tell you. This is definitely going to be the case. And of course, like concrete design, steel design, or timber design, we're going to have a lot of symmetric structures, okay? Or a lot of symmetric problems that we deal with, okay? So I mentioned that just to throw that out there. Yes?
When talking about symmetric, are you just ignoring if it's on a roller or a pin?
Great question. The answer is yes, and I'm going to tell you why. I don't care whether this is a hinge support, or a pin support, or this is a pin support for this problem. Why? Because that reaction is 0. It doesn't matter. So, if there is a horizontal load, though, then the problem is probably not symmetric anyway. So, it's a great question. And please don't hesitate for today. Today I'm throwing a lot of math and a lot of equations at you, so I really want to make sure you're absorbing the context. Okay. Sound good? Origins at the free end. Okay? Okay. I have said this a number of times in this class, okay? And I want to be clear again in saying it. Okay, so rules 2 and 3 have a lot common in their motivation. If I have beam over here, beam A, and this beam is subjected to loads, and I want to find the deflection right here, okay? This beam does not care how Greg or Kyle decides to do the computations. The answer is the answer, okay? Do you like the Greg or Kyle thing? Do you like that?
It's all
The beam doesn't care. The answer is the answer, okay? But that doesn't mean that you can't make your life easier, okay? So I want to show you some examples. Okay, let's take a look at this. This was the very first problem that we did when we were looking at deflections. I have a cantilevered beam. I have 2.5 kips per foot distributed load, 15 foot long. Here's the E value, there's the I value. And I think the deflection was something like 0.911 inches, something about like that. Okay? Is there any difference between these two beams? What's the difference between this beam and this beam? On the left and right, what's the difference? The Where's Waldo game. What's the difference between these two pictures?
Their support is different and
The support is on the right over here, it's on the left over here, okay? Now, does that create a different physical structure? I say no. In other words, like, look, imagine that beam is right here. So I'm standing here looking at you, the support's over here, okay? So here's the beam. What if I do this? Now the support's over here, but it's the same beam. The beam didn't change, okay? Do you like that? The YouTube audience doesn't get to see that. So. But okay, in all seriousness, though, my little, trot around the beam did not physically change the performance of the structure. It didn't physically change any of the characteristics. So here I've got so I put the coordinate system on the left end of the beam. So, think of like my XY axis. The origin's over here, the origin's over here. The only thing I did is I moved the support over to the other side. Okay? What does that do? Okay? Let's assume that the origin is over here at the free end. Okay? So I cut a section, look this way. This is what we did in class. I got a big M of negative 1.25x squared, a little m of negative x, multiply the two. So my deflection is computed as follows. I integrate from here to here, and then my deflection is that integral divided by EI times 1728, and that's what I got. Right? That's what we've already done that problem. We did that in class. That's exactly how it worked out. Okay? Right with me on that? Now, let's put this over here. Let's put the support, let's flip it. Let's put the support over here. Well, first off, if I cut a section, look to the left, I have to deal with the supports. I have to deal with the reaction in the vertical direction and the moment reaction. So if I cut a section, look this way, my big M is going to be a lot more complicated. My little m is going to be a lot more complicated. So I've got this nonsense I have to integrate. But here's the funny part. If I integrate this from 0 to 15, I get that. If I integrate this nonsense from 0 to 15, I get the same answer. The beam doesn't care. The answer is the answer, okay? I'm saying that I did a much easier problem than you would have done if you put the origin here, okay? The tip is to put the origin at the free end because you don't have to deal with all this nonsense, okay? And I'm not saying that'll always work in every case, but more often than not, if you're defining the origin at the free end, less algebra, less nonsense. Does that make sense? Again, beam doesn't care if you flip it over. Doesn't care. And one thing I want to say is, look, your job as structural engineers is going to be to design beams, to size elements. Your boss isn't going to tell you to put the coordinate system in certain ways. Your job as the engineer to define the model the way you see fit. This is more about big picture stuff. How do you set these problems up in a way to make them easier to do? Make sense? Tip 3. When cutting a section, always look toward the origin. Okay? So, here's the problem. Okay? So, let's take a look at this. Okay? And you agree with me based on tip 2 to put the coordinate system at the free end. So there's the coordinate system at the free end, okay? So put the coordinate system at the free end. Now we need to break out the samurai sword or the lightsaber. Okay, we got to cut a section. I'm sitting on top of the table. He breaks out the samurai sword, cuts through the table. I fall down. The reason why is that inside the table, at the point where the section was cut, there were internal forces and moments keeping me upright. It doesn't matter whether you investigate the equilibrium on this side of the cut or this side of the cut, because the beam was seeing the same thing right here. You released the same response at the point where you cut the section, okay? But again, that doesn't mean you have to make your life more complicated, okay? So I propose that more often than not, when you cut a section and look toward the origin, it's easier. Let me show you. Let's look toward the origin, okay? So the origin is right here, okay? Now, the beam is how long? 15 foot. So this is X. What is that? 15 minus X. Okay. So when we cut a section and we look to the left, what do we got? We got, let's see, cut a section, look over here, we got the distributed load, got this, got the shear, got the moment. So we sum moments at the cut, okay? So what do we have going on? Okay, so we're cutting some moments right here. We don't have to consider the V. We have M going this way, and then how do we characterize this load? It is a force times a moment arm. How much force comes from this load? It's not 2.5.
2.5x.
2.5 times X times a moment arm of?
X over 2.
X over 2. So we get this, we solve. Simple, right? Okay. Now what happens if we look away from the origin? So we cut a section, look to the left. What happens if we cut a section, look to the right? Well, okay, let's do that. So we cut a section, look to the right. We have to deal with all this. Okay? So, some moments. So what do we have? We've got M going this way. Okay, now let's talk about this force. What's the amount of force? Is it 2.5x? No, it is 2.5 times 15 minus x times a moment arm of 1/2 of 15 minus x. So I have to consider all that. I also have 281.25 on there. Opposing the other direction is 37.5 times 15 minus x. Now watch this nonsense. So, okay, so we have M plus this, which 2.5 over 2 is 1.25, 15 minus x, 15 minus x, plus that equals this. Algebra land. I see some foiling we need to do over here. So first times first, 225. Outside negative 15, inside negative 15, negative 30, plus x squared. Over here on the right, 37.5 times 15 is this, 37.5 times that is that. Let's distribute this one out. So 1.25 times this is that, 1.25 times this is that, 1.25 times this is that. Okay? Let's collect some like terms. So we have m of x. This is the x squared term, the x term, the constant, no x squared term, that's the constant, that times that. What can we do? Well, we can cancel out that, and we get the same answer we did on the last slide. So there's this way of doing it, or there's my suggestion, which is to cut a section and look towards the origin. You see what I'm getting at? Listen, what I'm talking about is there are strategies that you can use during a homework exam, during an exam, that can avoid this nonsense. That's what I'm trying to get you to avoid, is having to do all this. So there's a reason why the problems we've been doing so far, we've been putting the origin on one side, we've been cutting a section looking towards the origin. This is why. This is what happens when you don't do that. Okay? Does that make sense? Okay. I want to be clear that, again, the problem doesn't care. Okay? The answer is the answer. You will get the same answer regardless of which direction that you look if you've done the math properly. But there are ways to make your life easy. Looking towards the origin usually results in a lot less algebra. Okay. Sound good? Tip 4. Exploit integrals with a lower bound of 0. Okay? And what do I mean by that? I mean an integral from 0 to 8, or an integral from 0 to 16. Okay? Why am I talking about that? Why am I talking about lower bound integrals with 0? Okay. Let's consider this beam. Okay? All right. So I have a beam with a load on it, and for the sake of discussion, it doesn't really matter what the load is. It could be uniformly distributed, it could be a function, it doesn't matter. So just some load W on the beam. Now there is no way of avoiding the ability or the need to do two integrals. You're going to have to do two integrals, because if I look at my moment diagram, I'm at least going to have, maybe sort of a parabola like this and sort of another parabola like that. Like there's no way of getting around the fact that I'm going to have a function, let's say, from here to here and a function from here to here. I'm going to have to do two. Okay. All right. We, hopefully the past couple of tips have shown you that we can put the coordinate system wherever we want, and we can orient it however we want. Well, if we can do that, why don't we just use two coordinate systems? Why don't we put a single coordinate system this way and a coordinate system this way? So we'll actually have two coordinate systems. So imagine like one coordinate system with the origin over here and one coordinate system with the origin over there. And all this is doing is just flipping it that way. Okay? Now, why do that? Because I'm sure some of you are seeing that and going, well, Dr. Mike, that looks more complicated. I disagree. Okay, let me show you. Let me show you what I mean. Okay. A lot of what we are integrating in this class are polynomials. Okay? So let's have ourselves a nice little calculus lesson up here. So let's integrate ax squared plus bx plus c from 0 to, I don't know, t. It doesn't really matter. Okay, somebody help me out with this. What's the integral of ax squared?
A over 3x cubed.
Ax cubed over 3. Plus, what's the integral of that?
Bx squared over 2.
Oh. Plus cx. This is a definite integral. So this is evaluated from 0 to t. How do I do that? How do I evaluate from 0 to some value? I mean, how do you do a definite integral? You plug in the top number minus plug in the bottom number, right? So what's that going to look like? It's going to look like at cubed over 3 plus bt squared over 2 plus ct minus what?
0.
What was that? Minus 0. The fact that this bottom number is a 0 makes all that go away. Does that make sense? So, again, how do we do a definite integral? We plug in the top number minus plug in the bottom number once we've gotten our antiderivative. The plug and chug aspect is a lot easier. And I put an example here on the slides, like if we were doing this integral, if we were integrating that from 0 to 4, we would say, okay, let's integrate it from 0 to 4. So This is 2x to the fourth, this is 2x to the third, this is 5x. Plug in the top number minus plug in the bottom number, but all that hullabaloo on the right is 0, so we just get left with the final answer. So using a lower bound value of 0 makes the math a lot easier to do. So going back to this problem, what I'm saying is if you're using only one coordinate system and you're using just the coordinate system over here, you're going to have to do two integrals, one from 0 to 30, like 0 to 30, and one from 30 to 46. But I propose that if you use two coordinate systems, you can go from 0 to 30, you can integrate this way, like using this coordinate system, integrate this way, and then use another coordinate system integrating the other way. As long as you sum up the entire beam, get the energy along the entire beam, it doesn't matter. So we'll have one integral going from 0 to 30, and then another going from 0 to 16. There's that 0 lower bound. This integral will be a lot easier to chug out. Also, doing it this way, these functions written in terms of x2, as opposed to these functions written in terms of x, these will probably be a lot more gentle algebraically than these. These will probably be a mess. These one will probably be easier to deal with. So you've got simpler functions to integrate and a 0 that you get to plug in. I love plugging in 0. It's easy to deal with. Okay? Does that make sense? Okay. One note on flipped coordinate systems, though, just like you gotta be careful with this, is that you can still, like if you're dealing with little m functions or big M functions and they are lines, that's fine. The big thing you gotta keep in mind is you gotta flip your slopes. So the slope comes from the shear diagram, but keep in mind you're also flipping the direction in which your change of x goes. So if you have this line on a different coordinate system, if you orient the coordinate systems the same way, the line gets flipped the other side. So in other words, if you want to use the point slope formula to get your moment equations, just change the sign on the slope if you're flipping the coordinate system. So again, you can get around all that by just cutting sections, but just wanted to throw that out there. Okay. All right. Just to show you a quick little interactive example here, and I believe I've got a lot of this solved out here in the slides. Did I say that here? Oh, I did. Yes. Okay. So let's take a look at this somewhat like, this is kind of a nasty problem. Okay. So let's say I want to compute the displacement at C and the rotation at E on this beam. So this is a really, really nasty problem. There's a lot going on here. Okay. So some observations like before we begin. So notice how I put two coordinate systems on either end. So I've got an x1, y1, and an x2, y2. So sort of an origin looking this way and an origin looking that way. Okay. So how many moment functions are we going to need for the real moment diagram? We're going to need 3, because we're going to need one from here to here, here to here, here to here. We're going to need 3. Okay. We're also, again, we're going to use those two coordinate systems to make our life easier as much as we can. Let's see. So let's see if we can game out what our coordinate systems are going to look like. And this is the plan I'm going to use for this problem. Okay? So my first moment function, which is going to be sort of this piece of the moment diagram, I'm going to use this coordinate system from x equals 0 to x equals 10. The second coordinate system, this one right here, to be honest, it's probably like a coin flip as to which coordinate system would be easier to deal with. I'm just going to go ahead and say it's going to be this one. So the first one will be from 0 to 10. This next one will be from 10 to 40. I don't know why the coordinates are left up there. And then the last one will handle this part right here. Okay. So one thing I'll say is I'm not going to go through every single step here. I'm just summarizing the formulas and the computations. But I would attempt to see if you can derive some of these on your own. I'm giving you a big comprehensive set of answers here. So let's consider the real structure. So this is what the structure looks like. These are the reactions that you solve for. This is what the moment diagram looks like. So you have a linear moment diagram here, a quadratic one here, a quadratic one there. Okay. And when you chug it all out, this is what you get. Okay. So you get M1 is a line, so it's just a line with a negative slope, so negative 20 times x1. This M3, because we're cutting a section and looking this way, this M3 is really, really easy. It's just negative x squared. One thing I'll say is M2, I did a little bit of algebra here to make this one a little bit sort of easier to fit on the slide. So if you do this problem and you get a somewhat nastier version of M2, that probably happened, that's okay. I did a little bit of algebraic manipulation to get it to this form. Okay, that's our real structure. Okay, what about our virtual structure? Okay, so our virtual structure, if we're trying to find the vertical deflection at C, I put a single point load there at C. I get half and half. So that's what my moment diagram looks like. So what do I get? Okay, from A to B, the moment is 0. From D to E, the moment is 0. Okay, and from here to here, I get 2 lines. Okay, so for example, if I go back here a little bit, on the real structure, I'll have a single function that works for this whole parabola, but on the virtual structure, I've got to have a line that goes from here to here and a line that goes from here to here. So I got a little bit more going on here on the virtual structure. So I've got a line with a positive slope there, line with a negative slope here. Everybody okay with that? So, how do we do those computations? Again, you can do it in a table, you can do it as separate integrals, however you want. So, here are going to be my ranges, A to B, B to C, C to D, and then E to D. I wrote it E to D because I'm going that way, I'm going backwards. So, the way I wrote the ranges, this is in terms of x1, x1, x1. This one's in terms of x2 going the other way. Again, I wanted that lower bound integral. Here's the real moment functions. Here's the virtual moment functions. Notice how a couple of them are 0, okay? So when I carry out the integrals, that's 0 and that's 0, okay? For the 2 in the middle, if I integrate 10 to 25, 25 to 40, so I only have 2 I have to integrate. Sum that up, I get that. There's my answer. Does that make sense? And don't worry, I've got these slides on Blackboard for you. For the rotation, I'm just going to put a single unit moment right here. So a single moment this way, I have to get a single unit moment the opposite direction. So that's why I have equal and opposing reactions. My moment diagram goes linear, constant, and then a sudden jump back down. So I have 0 moment here, a linear moment there, constant moment here. Set up the same table. Do kind of the same thing. I don't have to have 2 separate virtual moment functions right there. So there's my range, there's my functions, there's my virtual moment functions. So likewise, that first one is still 0. Carry them out, sum them up, get this. The only thing that changes in the process is the fact that since I'm doing rotations, I'm using 144 times 180 over pi. That divided by EI times 144 times 180 over pi equals about 0.141. So my answer is 0.141 degrees rotated over. That was a really nasty problem, but I wanted to give you a really nasty problem and give you a guide that you could follow when you're doing your assignment. This one, I believe, is much nastier than the problems I gave you on your homework assignment. I think if you can do this one, you can definitely do the homework assignment. So,
I have a question for the homework.
I have an answer.
Do you recommend that we construct the shear moment diagram for the homework problem?
Yes, I do. And let me pull this up. So, now let me say this. I'm going to give you 2 answers as to why I'm suggesting that. Okay. So let me let's make this a little bit bigger. Okay. So a couple things to keep in mind. Okay, I actually got 3 answers. Okay. So let me give you my 3 answers. First answer, you may not need to construct a shear and moment diagram, but it does help to see it. So let's take problem 1. Okay. Problem 1. What is the moment diagram going to look like from here to here and from here to here? What shape is it going to be? It's going to be linear, it's going to be cubic. What's it going to be from here to here and from here to here? If I have a uniformly distributed load, what is it's a constant load, what does the shear diagram look like? Constant loads mean linear shear. Linear shear means what type of moment?
Quadratic.
Quadratic. So that means that my moment function from here to here and from here to here better have an x squared in it. You get that from constructing the moment diagram. So that would be point 1. Okay? Point 2. The purpose, so in order to construct a shear diagram, in order to construct a moment diagram, you need reactions, right? I need to know what the vertical reaction is here, what the moment reaction is here. Same thing here and here, okay? If my functions are correct, then if I plug in, let's take the problem 1. If I derive a function and I plug in x equals 30, I should get the moment reaction there at the end. So that's a second reason why actually drawing the shear diagram, actually drawing the moment diagram will give you a check on your work. Third, particularly for this problem, I mean, I don't know that drawing the shear and moment diagram would technically help, but if I have a moment function where this is the origin and I plug in x equals 16, what should I get right here?
0.
0, because it's a hinge. So, constructing my moment diagram, I should have a 0 at the hinge, and my function should yield a 0 at the hinge. So those are like 3 reasons why. They will qualitatively tell you what your function should look like. Getting the quantities from your shear and moment diagrams will help you check your algebra. And 3, they should both cross 0 at the hinge. That's why I suggested so. You are going to need to cut a section here and look this way to get reactions and whatnot. So, but again, yeah, you notice I put a coordinate system on this one. I did not put coordinate systems on this because you can use a coordinate system here and a coordinate system there.
I have a second question.
All right.
So for the first one, when we're cutting the section, does it matter if we cut before or after the 30 kip?
Ooh, that's a great question. Let me let's think it through though.
Okay.
So, how many moment functions are needed to fully define this moment diagram? How about this? Anytime there is a change in load, there is an interruption in load that requires another function. So, if I start dragging this way, so look at this side of the beam. Distributed load, distributed load, distributed load, distributed load. Boop, now there's something different. I'm saying you're going to have to cut a section from here to here, look this way, cut a section here, look that way. 2 different equations. Because it's 2 different parabolas.
Okay.
But be clear, that's for the real structure. For the virtual structure, all of those loads are going to be gone, and the only thing you're going to have is a point load right there, or a unit moment right there. So are you going to need to cut a section twice for the virtual structure? No, because the real structure is going to have a function from 0 to 10 and 10 to and another function from 10 to 30. The virtual structure, just one function for the whole thing. Those are good questions. Any other questions? This is good stuff. I like this stuff. This is probably the most algebra and calculus heavy assignment we have this semester. If it makes you feel better, influence lines, there's hardly any of this stuff. So influence lines are very much a look at the problem, that's the answer. So, any other questions? I'll see you on Wednesday. We'll talk about brains.